So, in velocity, what kind of things can we come up with about what's happening to that proton? Laura, can you tell me something? Tell me something that we could calculate about the proton without knowing anything else. If I tell you a proton's at that velocity, what can you tell me? You don't know. So, what is that? Velocity. Any object that has a velocity has what? Sorry? What kind? Kinetic energy. So, we can say that this proton has a kinetic energy that's 1/2 mv squared, right? Now, is that going to be useful? I don't know. I'm just saying, like, we should be looking at that kind of thing when we look at this problem, or any problem where we say, okay, it has velocity. You should be going through, okay, it has a kinetic energy, it has a momentum, right? Those sort of things. Now, what in the world does this mean when we go from A to B? What are these things? Let's see, Manal. What are these lines? Sorry? What are these three lines? Have you seen something like that before? Okay, good. He's working it through pretty well without remembering what it was we talked about. So he's saying these are like graphs of points that all have the same electric potential. What are those called? Those are equipotential lines. These are equestrian lines. Come on. Isn't it obvious? The horse jumps over this one, then it jumps over that one. Okay. So these equipotential lines are places where you can say everywhere along that place has the same electric potential. And what does electric potential mean? What does that term mean? If you're not sure, just think of the units. What units are those equipotential lines, Fonja? Yeah, it's obviously volts. It says right there. So, Fonja, what is a volt? A volt is a what? A what? Ribbit? Joule per what? Yes, joule per coulomb. Very nice. Funny. Okay, so a volt is a joule per coulomb. So I was talking to Alan about this the other day. When I think about electric potential, and I try to think, what does that mean? Right? For me, I think of electric potential almost as like gravitational acceleration. Right? Like everyone in this room, do we all have the same gravitational acceleration? No.
Yes. Oh, you mean towards the floor.
Right? Because is it not reasonable for us to say, well, okay, how about this? Oscar, why do we all have the same gravitational acceleration? Okay, Oscar says because we're not accelerating, we're just standing here. Okay. In fact, are we accelerating right now, Sherman? Yes. And which way are we accelerating? How do you know we're accelerating down? Because we're not flying off into space at 1,000 miles an hour. The Earth is rotating at some 1,100 or 1,000 and change miles an hour. If there was no gravitational acceleration, we would fly off. Does this make sense? Let's go. Yeah. You may enjoy the, 4 Kelvin, zero pressure of space, but I don't want to actually find out if the blood's going to squirt out my nose before it freezes or not. I prefer not to find that out.
Which hole in the body will it come out first?
I know. It's like plug your ears. I saw that in a movie. Did that really work? This guy had to jump across this part of space.
Wouldn't you just go?
No. Because without pressure, your skin. Am I recording this?
What if your
Awesome. Okay, sorry. All right. So.
We're recording it?
Yeah, I was recording that. All right. The more important thing is, right now, we all have the same gravitational acceleration. Why? Alan do.
Because we're being affected by the same gravity.
Okay, same planet, but hey, if we compare, I don't say Laura and myself, there's a lot more of me than there is of her. So how could we possibly have the same gravitational acceleration? Randy, you help out? Okay, we've reasonably ascertained that, right? Because we're both sitting here. Daniel, what do you got? Can you help? Daniel's honest. Daniel, how do you calculate the gravitational acceleration? Yeah, how do you find that? Is this still recording? I'm turning this. I forgot to record this.
Oh, they're gonna record my stupid response.
Okay, sorry. Say that again, real. Why do you say lose?
Because it's going from 30 to -10.
Okay, so what does positive and negative mean for this?
Oh, it's a scalar.
Or is it just going the other way?
Sorry.
Wait, give me a second. Alright. Wait, what was the question?
Yeah, why is there what's the difference between these two? 30 and -10.
Just the amount of energy there is. Because the charge is already set. Right. Well, yeah. Because the charge of the protons is already set, so the energy level is changed.
Yeah, so it kind of says what's going to happen in terms of how our energy gets distributed to the charge, right? Because like you're saying, this charge is already set up. So if we have 30 volts or -10 volts, when we want to calculate the effect, then it's going to depend on what the charge is that we're putting in. We're putting in a positive charge, right? Because it's a proton, and then this difference, the delta V, is 40 volts. So then, how much energy is that is it gonna give or take away energy from this charge? That's ultimately the question, right? Interesting. Let's do this. Oh yeah, but they're just asking between A and B. Yeah. So I'm sorry. Let me make sure that I'm clarifying. Do we see that the question is specific point A to point B? What happens? And I believe they're telling us at point A, it has that velocity. Yeah.